The directions say to solve the given differential equation. The focus in this video is on Cauchy-Euler equations. Let's take a look at example 1. Suppose we're given x squared y double prime minus 2y is equal to 0. So for this type of equation, we're going to set y equal to x to the m. Y prime is mx to the m minus 1, and y double prime is equal to m times m minus 1, x raised to the m minus 2. Now we get to make our substitution back in. So we get x squared times y double prime, which is m times m minus 1, x raised to the m minus 2, minus 2x to the m equals 0. Now, I'm going to distribute the m inside here, and when I do, I get m squared minus m, and I'm going to take this and multiply by x squared times x to the m minus 2, and by design, it's equal to x to the m. And then I'm going to subtract 2x to the m and set this equal to 0. When I factor out an x to the m, I get x to the m times m squared minus m minus 2 equals 0. But x to the m does not equal 0. So therefore, m squared minus m minus 2 equals 0. When I factor, I get m minus 2 times m plus 1 equals 0. Solving for m, I get m equals 2 or m equals negative 1. So my two linearly independent solutions are y, we'll call it y sub 1. So y sub 1 is x squared, and y sub 2 is equal to x to the negative 1. So my general solution will be y equals ax squared plus bx to the negative 1. That's example 1. Let's take a look at example 2. Suppose I had 4x squared, y double prime, plus y equals 0. So y equals x to the m. Y prime is mx to the m minus 1. We need y prime to get y double prime. So y double prime is m times m minus 1, x to the m minus 2. Just like in example 1, now we get to make our substitution. So 4x squared times m minus 1, x to the m minus 2, plus y, which is x to the m, equals 0. Now, I'm going to distribute the m inside to each term within the parentheses. And when I do, I get 4 times m squared minus m. And then x squared times x to the m minus 2, again by design, is x to the m. Plus x to the m is equal to 0. I still need to distribute that 4 inside. So when that happens, I get 4m squared minus 4m x to the m plus x to the m equals 0. I'm going to factor out an x to the m, and when I do, I get 4m squared minus 4m plus 1 equals 0. But x to the m does not equal 0, and so therefore 4m squared minus 4m plus 1 is 0. And when I factor, I get 2m minus 1 raised to the second equals 0. Now, when I solve for m, I get m equals 1/2 twice, like so. Now, one solution will be y1 equals x to the 1/2. Now, my second solution has to be independent of my first solution. So in other words, y1 and y2 have to be linearly independent. Now, if I just put y2 equals x to the 1/2 because I got 1/2 twice, y1 and y2 are not linearly independent. And it turns out we can show that if I just take y2, well, let me say it this way. If I take x to the 1/2 and multiply by natural log of x, we can show with the Wronskian that y1 and y2 are linearly independent. So what I'm going to do is take x to the 1/2 and multiply by natural log of x. And now I've accomplished my goal. X to the 1/2 and x to the 1/2 natural log of x are linearly independent. And so my general solution will look like y equals ax to the 1/2 plus bx to the 1/2 times natural log of x. And that's example 2. Let's take a look at example 3. Suppose I had x y double prime plus y prime equals 0. So just like in examples 1 and 2, I'm going to set y equal to x to the m. Y prime is mx to the m minus 1. Y double prime is m times m minus 1 x to the m minus 2. So when I make my substitution, I get x times y double prime, which is m times m minus 1 x to the m minus 2, plus y prime, which is mx to the m minus 1, and that whole thing is equal to 0. So I'm going to distribute the m to each term within the parentheses, and when I do, I get m squared minus m, and then x times x to the m minus 2 is x to the m minus 1, plus mx to the m minus 1 equals 0. So if I factor out an x to the m minus 1, I get, if we go back, I get m squared minus m plus m. And so x to the m minus 1 is not 0. And so therefore, m squared equals 0, and which says m equals 0 twice. And so just like in the first two examples, I need two linearly independent solutions. Well, one solution will be x to the 0, which is 1. My second solution will be, if you don't mind, I'm going to call it 1 times the natural log of x. So when you have a repeated root, that's how we compensate for that. So my general solution will look like y equals a plus b times the natural log of x. And that's how we do example 3. Let's take a look at example 4. Suppose I had the following. Suppose I had x squared y double prime plus xy prime plus 4y equals 0. So we're going to set y equal to x to the m, y prime is mx to the m minus 1, and y double prime is m times m minus 1 x to the m minus 2. So let's make our substitution, just like in the first three examples. I have x squared times the quantity m times m minus 1. First, we'll say m times m minus 1 x to the m minus 2 plus x times mx to the m minus 1 plus 4x to the m equals 0. Okay? Now, if I take m times m minus 1, I get m squared minus m. And that's going to be multiplied by x to the m plus mx to the m plus 4x to the m equals 0. Now, if I factor out an x to the m, I get x to the m times the quantity. So I'm going to get m squared minus m plus 4. M squared minus m plus 4. This is equal to 0. X to the m is not 0. And so what that tells me is m squared plus 4 equals 0. So m squared equals negative 4. And then m is plus or minus 2i. So notice how we have two complex roots, right? Plus or minus 2i. So in this case, notice that my alpha equals 0 and beta is equal to 2. Okay? And it turns out that we can show that my two linearly independent solutions are x to the 0 cosine of 2, that's beta, natural log of x, which is equal to cosine of 2 natural log of x. And my second solution is x to the 0 sine of 2 times the natural log of x, which is equal to sine of 2 times the natural log of x. So my general solution will look like a cosine of 2 natural log of x plus b sine of 2 natural log of x. And that was example 4. And that'll conclude this video on, it's a differential equations video where we solved 4 homogeneous differential equations that were Cauchy Euler. So, okay, thank you.